right, take your homework out and turn your textbooks to page 129. You wrote out the double angle identities 2 times each. And you also did page 129, numbers 19 to 24, using the Part A information. Good. There's your double angle identities. Oh, you did Part A, B. Oh, you started to do Part B and C and then caught yourself. Okay. Yeah, I was about to say, man, that's a lot of time. Bless your heart. All right.
You know he likes to put them all away.
It's true. It's true. You know, he's just trying to show off and keep that favorite student status.
No, I'm the favorite
All
student.
right. Oh, that's right. That's right. You're back to favorite student. Well, he was trying to get it back. He had it that one day when he did the identity correctly. All right. Let's go ahead and review over our double angle identities very quickly. For the sign, let's pick a Greek letter here, Ethan.
The circle with the line through it.
Phi?
Yeah, phi. Yeah.
Okay, so the sign of 2 phi, what is our double angle identity class? 2 sine phi cosine phi. Okay?
There's no jingle for this one, is
There isn't. Okay. Now let's go with cosine. Pick a letter.
Alpha.
Of 2 alpha. There's 3 different ways we could do it, but the first one that I told you to know, this is probably the best one to know, is cosine squared alpha minus sine squared alpha. But, pick a letter, Quentin.
Mu.
For cosine 2 mu, another way we could write it.
1 minus cosine squared.
2
Or 2 sine squared.
sine squared mu. So we double up on the sine squared and we replace it with a 1 because this becomes 1 minus sine squared from the Pythagorean. Or pick a letter, Chris.
Is Foxtrot a letter?
No.
Okay, gamma.
2 gamma.
Lowercase.
Yeah, right. And so, Foxtrot would be in the phonetic alphabet for F, but it's phi in the Greek alphabet. The other way we could rewrite the cosine double angle would be
2 cosine squared gamma minus 1.
there we go, 2 cosine squared minus 1, where the sine squared would be replaced with a 1 minus cosine squared. And then, of course, it comes out to this. So a few ways we could rewrite cosine double angle. And then the last one was the tangent double angle. Pick a letter, Ethan.
Omega.
And for this one, again, you're thinking of the tangent plus tangent all over 1 minus tangent tangent, but it comes out, class, 2 tangent omega over 1 minus tangent squared omega. All right, 2 tangent over 1 minus tangent squared. So sine, cosine, sine becomes sine, cosine plus cosine, sine. They're the same thing, so it's 2 sine, cosine. Here, cosine, sine, sine. Cosine squared minus sine squared. Again, a couple of Pythagorean identities get us these alternate forms, and then here it's tangent plus tangent, or 2 tangent, all over 1 minus tangent tangent, or tangent squared. We were using these then to do numbers 19 through 24 using Part A. We were told that the sign of phi is 5 to 13. We were also told that phi lies between pi over 2 and pi. In other words, what quadrant is phi in, class?
2.
Quadrant 2. So, when we want to find the sign of double phi, twice phi, well, a quadrant 2 angle, if you double it, would either go to... Bless me. Thank you. All right. I feel blessed. Thank you, Chris. Favorite student. All right. So when we double a quadrant 2 angle, class, we will either go into quadrant 4 if it's a big quadrant 2 angle, like say 170 doubles to say 340, or a small quadrant 2 angle to actually double into quadrant 3. Like for instance, a 100-degree angle would go to 200. So 2 phi could be quadrant 3 or quadrant 4, we're really not sure. But the signs, SIGNs, will take care of themselves. All I have to do for sine double angle is write out the identity first, class.
2 cosine theta sine.
2 sine phi cosine phi. Let's say that together, class. Sine of 2 phi equals 2 sine phi cosine phi. All right? Now we plug in the numbers. And the sine of phi, of course, is 5 to 13. No problem there. What do I plug in for the cosine of phi? Well, we got to figure it out. Of course, we know sine is what over what, class? Hypotenuse. So we're missing the... And you should have found the adjacent for theta to be what, Jamie?
12.
12. So what was the cosine of phi, Quentin?
12 or 13.
12 to 13. But remembering that phi is in quadrant 2, the cosine would have to be negative. I would also write the 2 as a 2 over 1 for multiplication purposes. So I end up with what right here, Chris?
Negative 120 over 169.
Negative 120 over 169. How many had that for the sine of 2 phi? Now that, by the way, doesn't tell me what quadrant we're in, because sine would be negative either quadrant 3 or 4 anyway. So 2 phi still could be either one. Once we have the cosine 2 phi, let's go and get the cosecant 2 phi right away. Class?
Negative 169 over 120.
Yeah, negative 169 over 120. So we get both answers really quickly. Okay? Questions on sine and cosecant. Do we have those answers? All right? No?
No.
All right, does it make sense now?
Yeah.
All right, let's go then to the cosine of 2 phi. And again, my recommendation is, in general, go with the first form. I just feel like that's going to be easier for you. Unless we're working an identity, and we're going to look at some of these today, where you don't want cosine or you don't want sine. Then you kind of got that already built in to take care of you. But for the cosine 2 phi class, our identity is cosine squared phi minus sine squared phi. Again, cosine 2 phi equals cosine squared phi minus sine squared phi. Now we already know the cosine of phi is the negative 12 to 13. We just got to square it. Ethan?
Okay, 169 over 25.
We're squaring the cosine of phi.
That was 13.
144 over 169.
There we go. So we get a 144 over 169. You didn't say negative, did you?
No, I didn't.
No, of course not. No, negative squared would be positive.
Yeah.
And then we already know the sine of phi is 5 to 13. But of course, we're going to square that, Jamie, to get
25 over 169.
There we go. And so to get the cosine of 2 phi, we just subtract, and we get, Quentin? You can use a calculator. 144 minus 25?
120 over, or 119 over 169.
Good, 119 over 169. How many have that for the cosine of 2 phi? Okay, only a couple of us this time. And then we need the secant of 2 phi, which we'll get right now. Chris?
169 over 119.
There we go. And by the way, notice cosine and secant came out positive. Apparently the doubled angle winds up in quadrant 4. Because cosine comes out positive while sine remains negative. And so does cosecant. All right, the last thing we need to find is the tangent of 2 phi. And let's write out our identity for the tangent 2 phi, class. 2 tangent phi over 1 minus tangent squared phi. Again, 2 tangent phi over 1 minus tangent squared phi. And so we will, in the top, do 2 over 1 times the tangent of phi. Well, what would the tangent of phi be, Ethan?
5 over 12. Quadrant 2, so negative.
Negative 5 to 12. And then that negative 5 to 12 is going to appear again in the denominator here, but it's going to be squared. And so we're going to have a 1 minus that squared. Well, here in the top, 2 times negative 5 twelfths gives us
Negative 10 over 12.
negative 10 twelfths. You say, ooh, we could reduce that. But remember, I told you as we looked at in the last lesson, let's not reduce yet. You'll see why in a moment. Here, when I square, I'm going to get, Jamie,
25 over 144.
a positive 25 to 144, which means I should rewrite the 1, Quentin, as
144 over 144.
144. So when I subtract 25 144ths from 144 144ths, Chris, I get
Negative or positive 19 over 144.
119 over 144. But of course, this is a complex fraction, and to divide a fraction, I really multiply by the... So Ethan, I'm going to change this to multiplication by a 144 over 119, and this is why I didn't mind leaving the 12. It's easier for me to cancel a 12 with a 144 than a 6 with a 144 to get 1 and 12. And so when I multiply negative 10 over 1 by 12 over 119, I get
120 over 119.
a negative out front here, 120 over 119, and there's the tangent of 2 phi. Then of course we need the cotangent of 2 phi, and of course that's easy, class.
119 over 120.
negative 119 over 120, which again supports the idea that 2 phi is in quadrant 4 because the tangent came out negative. Can't be quadrant 3. How many got those answers for tangent and cotangent? Great way to check, and I wouldn't use this to solve, I would use this to check. Another way to find the tangent of 2 phi would be sine over cosine, remember? We already know the sine is negative 120 over 169. We know the cotangent is 119 over 169. That allows my 169s to cancel. Negative 120 over 119. Now again, if you screw up these two, you're now doomed to screw up the tangent and you have no way to check, which is why I don't recommend finding the tangent by doing this. Find it the proper way, use that as a way to check unless you're about to run out of time on a quiz or test. In which case, gamble that you're right and go ahead and get the tangent that shortcut way, because at least you got your answers that way. Questions on the homework? Well, let's do part B. Let's do part B now. Go and write down your given information from part B. And what are we given, Chris?
That sine is 2f.
Part B for tangent. We're looking at the top of the page, page 129, where the homework was.
Yeah.
Part B, what are we told?
Oh, sorry. Tangent phi equals negative 2, 3 pi over 2 is less than phi greater than 2.
It's less than 2 pi. In other words, phi is between 3 pi over 2 and 2 pi. Practically speaking, Chris, what does that mean if phi is between 3 pi over 2 and 2 pi?
That's in fourth quadrant.
Fourth quadrant. Okay, which of course makes sense that tangent would be negative. But tangent's a ratio, class. Tangent's what over what?
Opposite
Opposite
over
adjacent.
Opposite over adjacent. Here I don't see a fraction, so let's put it over 1. There's the opposite. There's the adjacent, but I don't yet know the hypotenuse. What must the hypotenuse equal at your seats?
Square root of 5.
And Ethan already got it. Square root of 5. Very good. How many thinking the same thing? Maybe just not quite as quick. Any questions on where I got square root of 5 from? Shouldn't be, but wanted to give you the chance. All right, so then, when I find the sine of 2 phi, the first thing you ought to do, plus it gives you partial credit, plus it is a roadmap of what to do, is write out the identity for sine 2 phi. Class?
2 sine,
Two
theta,
sine.
cosine theta.
2 sine theta cosine theta, or in this
Or
case,
phi.
2 sine phi cosine theta. And so I always like to put the 2 over,
1.
and then what is the sine of phi going to be, Quentin?
2 times square root of 5 all over 5.
I'm not going to rationalize here. I think you'll have an easier time in life if you don't here. So let's just leave it as,
2 square root of 5.
but in quadrant 4, and the reason I'm not going to, class, is because when you come over here for the cosine, remember, it's also going to be over hypotenuse. You're going to have both square roots times each other, so it's going to knock itself out just fine. Well, how do we write the cosine of phi here, Jamie?
1 over square root of 5.
And that is positive because of the quadrant 4. So, when I multiply across the top, class, 2 times 2 times 1, 2 times 2 times 1, 4. 1 times square root of 5 times square root of 5,
22 times
square root of 25, which is
5.
5. And of course, positive times positive,
Negative.
and there's the sine of 2 phi. Make sense? Let's get cosecant of 2 phi.
It's just 5,
5
negative 5
over 4.
over 4.
Good, negative 5 over 4. As Staples would say, that was easy. At your seats, find the cosine of 2 phi. What do we write for the identity class?
Cosine squared phi minus sine squared phi.
Thank you, Quentin. Class, what do we write?
Cosine squared phi minus sine squared phi.
There we go. And for the cosine squared phi, again, that's going to be 1 over the square root of 5 squared. For the sine phi, that's going to be negative 2 over square root of 5 squared. What do you get when you square 1 over square root of 5? 1/5. What do you get when you square a negative 2 over square root of 5? 4/5. What's 1/5 minus 4/5?
Negative 3/5.
Negative 3/5. And there's the cosine of 2 phi. Did you have that? Questions? What's the secant of phi? Of 2 phi, excuse me.
5 over negative 5 over 3.
Negative 5 over 3. By the way, notice, the sine has come out negative. The cosine has come out negative. What quadrant must we be in? Must be in third quadrant when we double. So quadrant 4 is the original angle. When we've doubled it, it's pushed it all the way to the third quadrant. And then the tangent of 2 phi at your seats. Okay, a little too much glare from this. There we go.
How about that overtime win for the Ravens?
How about the Vikings taking you guys to overtime?
How about us being
That must mean they're about as good as the Colts.
how about us being down 14 twice and still win? Twice we were down.
How about who's going to be by Case Keenum?
Huh?
That's the Vikings quarterback.
All right. So what's our identity for tangent 2 phi class?
Tangent over 1 minus tangent squared.
So 2 tangent phi over 1 minus tangent squared phi. Now the nice thing is, what's the tangent of phi?
2 over 1.
Negative 2. Do I benefit from making it a fraction right now?
No.
Nah. So I'm just going to do 2 times negative 2 over 1 minus negative 2 squared. And in the numerator,
Negative 4.
and in the denominator, 1 minus,
Negative 2.
Positive 4.
Positive 4.
and 1 minus 4 is negative 3, and negative 4 over negative 3 equals 4 over 3. The negatives cancel, so there's the tangent of 2 phi, so the cotangent of 2 phi is 3 over 4. And there we go. So this is the interesting thing here that at least I think it's interesting. If you have a 1 and a 2, you get a square root of 5, right? And there's your angle phi. If you double it, of course, that's going to push you into the second quadrant, but your reference triangle, if you double that angle, ends up giving you a 3, 4, that's not drawn to scale. You end up doubling it. The doubled angle ends up giving you a 3, 4, 5 special triangle. So kind of neat. Though in this case, it was actually a quadrant 4 doubled all the way to quadrant 3. But yeah, so interesting. All right, questions on this. Do we feel like you could do this on a quiz or test? Write out the identity, plug in the numbers. Think we could do that? Not too hard.
Stick around.
Good. Let's take a look at number 30 now, and let's talk about let's look at some trig verifications that use double angle identities. Go ahead and copy down number 30 there at your seats. Again, we've seen trig verifications with doubled angles before. We've just always written a 2 alpha as alpha plus alpha. And when you go through the long way, we ain't got to do that no more. So this is going to be very nice. Number 30, we have 2 times the sine of 2 omega minus 2 times the tangent of omega equals 2 tangent omega cosine 2 omega. And here's the hard part. Both sides have a double angle. But which side is still more complicated?
Left side, there's two different.
Left side has 2 terms. Good, Chris. This side still just has 1. By the way, something I noticed about the left-hand side. There's a 2 tangent omega. The other side still has a 2 tangent omega.
They're negative, you can cancel them.
So I'm feeling, careful.
Oh,
So
no,
I'm
no.
feeling like I don't really necessarily need to change this too much, right? But somehow this 2 sine 2 omega is going to have to morph over to a cosine 2 omega somehow, some way. All right, so let's take care of this sine 2 omega business.
Could you make the sine 2 omega, the 2 omega, what is the 2 omega?
It's
there's
omega
I
times
got-
2. It's a double angle.
Oh, okay.
So what do I write instead of sine 2 omega, class?
2 cosine omega.
2 sine omega cosine omega. You gotta memorize it. Double angle for sine is 2 sine cosine. Minus 2 tangent omega. And the problem is if I leave that 2 tangent omega, I'm really coming up with nothing. So maybe we should also rewrite the tangent.
There's the tangent double angle. It's a fraction.
It's not a double angle.
Yeah.
So I don't need to write it as a double angle.
Sine over cosine.
I could just write this as sine over cosine. Let's do that much. And this is all over 1. Thoughts?
Distribute. No.
Well, not so much distribution. It would just be a 4 sine cosine.
Common denominator. Common
Can I
denominator.
cancel the 2 cosines? Is your question.
No.
Ethan says no. Why not, El Presidente?
One's a term, one's a.
They're both factors, but this isn't a multiplication problem, it's a subtraction. So I can't cancel there. What do we do if we try to subtract 2 fractions? Get a common denominator. Let's draw a big long line. What goes under the big long line?
Cosine omega. Or cos.
And to change a 1 into a cosine and multiply it by cosine. And what you do to the bottom, cow, cosine omega. So here I've got a cosine omega and a 2 being multiplied by 2 sine cosine. So what does that end up giving me?
2 cosine.
2 sine.
2 cosine times
4.
Cosine omega.
There we go. If you have an x times a 2 times a 2xy, that gives you 4x squared y, doesn't it? Because 2 times 2 is 4, x times x is x squared, and y doesn't have any friends. Well, 2 times 2 is 4, sine doesn't have any friends, and cosine is cosine squared. Here, I already have a cosine omega, right? So I don't change anything, just leave the
2 sine omega.
thoughts now.
You still can't minus the 2 sine away from the 4 sine.
I can't because it's not just 4 sine minus 2 sine.
And you can't cancel the cosine away.
I can't because this isn't a term and that's a fact, and that's just a standalone. So no, but what can I do?
There's a double angle I believe with sine.
There's not a double angle. There's no double omega, or double omega. There's double sine, but there's not double omega. So no double angles.
Cosine squared omega is 1 minus sine squared.
If I had a 4xy squared minus 2x all over y,
You can pull out an x.
I could factor out an x. For that matter, I could factor out a
2.
2x. I'd be left with 2xy minus 1, wouldn't I? Or 2y squared.
Or you can
minus
multiply the
1.
y from the
Or
numerator.
to divide
What do you do?
both ones by the cosine. Something like that.
Yeah?
Or you could divide both of them.
Well, if I divide them individually by cosine, I go right back to this again.
Oh,
We'll
yeah.
factor out a 2 sine.
There we go. Let's factor. Let's factor out a 2 sine omega that's common to both terms. What am I left with if I pull out a 2 sine omega?
Cosine squared.
Careful.
2 sine omega.
2 cosine squared omega minus 1.
All over cosine omega. There's a 2 that's common. Pull it out. There's a sine that's common. Pull that out. If I pull a 2 and a sine out of this, I'm left with a 2. The sine has been pulled out and a cosine squared. Pull a 2 sine omega out of a negative 2 sine omega, I got to negative 1. Careful in your algebra. Now, thoughts on this 2 cosine squared omega minus 1? We've seen 2 cosine squared minus 1 before.
Cosine 2.
That's cosine double angle. So this whole parentheses just becomes
Sine squared omega.
Cosine 2 omega.
cosine 2 omega. That's what all that becomes. And I've got a 2 sine over cosine. Well, what is sine over cosine?
Tangent.
Tangent. So that's 2 tangent omega, 2 tangent omega, cosine 2 omega. That's exactly what we wanted. But we've got to be very careful with our algebra. Factoring, common factor, stuff we did in Algebra 1 last week. With the Algebra 1 class out with you guys. Yeah, factoring out a common factor. But again, instead of, it's not, to take you back to your old days, right? Here we'd say, what's common, class?
An A and 2 x's.
An a, 2 x's, and a 3. Pull a 3ax squared out of a 3ax squared.
And
1. Pull a 3ax squared out of a negative 12a cubed x squared.
Negative 4a squared.
And by the way, while we're on the review note, Ethan, what is 1 minus 4a squared?
That's a, would that be some difference?
It's going to turn into a sum and difference, right? So we would keep the 3ax squared, don't lose it, and factor this
Yep.
into
Do one, negative, positive, 2a and 2a.
Yeah, remember this stuff? But now, folks, it's not an A. It's like a secant alpha.
Yep.
It's not an x squared, it's a tangent squared omega. So that means this would be like a secant cubed alpha and like a tangent squared omega. But you see there's still a 3 common, there's a secant alpha common, there's a tangent squared omega common. Same kind of thing. I've got a 2 common, I've got a sine common, so I can pull out the 2 and the sine. Do you see it now, the parallel between what you learned in algebra? Again, it's just not x's and y's, it's sines and cosines. And that's where you got to be careful. Let's take a look at number 33, copy it down. Well, let's get some more practice. Love Algebra 3. I had students ask me that, what's Algebra 3? How come there's not Algebra 3? I said, there is, it's pre-calculus.
Why is it just called that?
Because we work trigonometry and analytic geometry and in actual calculus concepts later, so sounds cooler to call it pre-calculus and more accurate to call it that.
$33.
33. Now, if I were to ask a first grader, which side of the equal sign, this or that, looks more complicated, they would say that side. But to the trained eye, you notice that these are all plain old lambdas, aren't they? Now, there's some sine lambdas and cosine lambdas and there's cubes and all that, but they're still all plain old lambdas. This is a 4 lambda. That's more complicated than regular lambdas. This is the more complicated side. So we're going to start with the sign 4 lambda. Christopher, stand next to your desk. 4 lambda, we ain't got no quadruple angle identity, do we? But 4 lambda could be rewritten, do this with me, as 2 times 2 lambda. Correcto, Mundo? And we do have an identity for a double angle sine. What is sine's double angle identity class?
2 sine lambda cosine.
2 sine cosine. But in this case, watch, it's 2 sine, what is being doubled? 2 lambda.
Oh.
Cosine 2 lambda. Seest thou what thou oughtest to do?
No.
Seest thou what thou wilt do next?
No.
Forsooth?
Yes.
You doth. You doth. Thou, you do. Alright? Because here we go. Here's another sine double angle. And a cosine double angle. And a lonely little 2. So we're going to keep the 2. Don't mess with the 2. How do we rewrite sine 2 lambda?
Sine lambda.
Nope.
2 sine lambda cosine.
2 sine lambda cosine lambda. Now, remember, there are 3 forms for cosine double angle. It just depends on what you want. If you only want sines, you do 1 minus 2 sine squared lambda. But I don't want only sines. If I wanted only cosines, I do 2 cosine squared minus 1. But I don't want only cosines. I want sines and cosines, so what should I write for cosine double lambda? Cosine squared minus sine squared. And in each case, what's being doubled? Lambda. Now again, if I have a 2 times 2ab times a squared minus b squared, you with me? I would say, well, really the 2 and 2ab should just be multiplied first to get 4ab. And really, I should distribute a 4ab into the a squared minus b squared, right? Except, here the 4 isn't distributed. So let's just multiply the 2 times 2 to get 4, and let's only distribute the AB. Well, again, if it were AB times A squared class, you'd get a cubed B. Well, here it's a sine cosine times a cosine squared. What does that give me?
Sine cosine cubed.
Sine lambda cosine cubed lambda. And when I multiply AB times B squared, what do I get? AB cubed, or negative AB cubed. Well, here, it's a sine cosine times a negative sine squared.
Negative sine cubed cosine.
Negative sine cubed lambda, cosine lambda. And boom, I'm done. It's super easy. It just looks awful. I start to see the algebra connection here. I'm trying to help you see what you used to do versus what you're doing now, and it's really all the same thing. Okay, start to see it? Questiones? Do you see what to do with a 4 lambda? Double 2 lambda. Does that make sense? What if you had, I don't know, like the cosecant of 6 theta? How could you rewrite that?
3 theta.
2 times 3 theta. So you do 1 over 2 sine 3 theta, cosine 3 theta. Does that make sense? Okay? Whatever is being doubled goes into 2 sine cosine, but since it was cosecant, 1 over that. Does that make sense? You just hope you don't have one like that. All right, let's take a look at number 38.
This one like that.
Number 38. And copyeth it down. Sine 3 row, that's row, row, row.
Where were we going?
Gently down the street.
Man.
Life is but a nightmare. Alright. Sine 3 row equals 3 sine row minus 4 sine cubed row. Which side is more complicated, Jamie?
I don't remember anymore. I'll go with the left side.
The left, because on the right you have plain old rows, and those are simpler than triple rows. So triple row wins out, even though it looks like it should be less complicated. We know in our heart of hearts it's more complicated, right, Chris?
Mm-hmm.
However, we ain't got a triple angle identity, do we? And I can't write this as double nothing. So instead, what I'm going to do here is write this as sine of 2 row plus row. Just like we used to do for a double angle before we knew double angle identities, we do row plus row. Well, 3 row, instead of doing row, because I ain't got nothing for that, I'm going to do 2 row plus row, which means I have a sum identity. What is my sum identity for sine? Sine, cosine, cosine, sine. What is cosine? Cosine, cosine, sine, sine, sine. I just said we have to finish.
What's both of them?
Faster.
What's both of them?
What's both of them together? Sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. But all we're doing here is sine, so class, just sine, cosine, cosine, sine. So we write down sine, cosine, cosine, sine. And then we drop in the 2 row, row, 2 row, row. That's a bad row. And we keep whatever SIGN was here, because there was no indication to change it to sine, cosine, cosine, sine. Follow so far? All right. I have a sine 2 row. Now that it's all just plain old double angle, I get to write out my double angle for sine. 2 sine row, cosine row. And it's being multiplied by cosine row.
Can we distribute all of them?
Well, distribution would be a polynomial times a monomial. And it's technically just monomial times another monomial. We'll get to that in a second. Then I have cosine 2 row. And there's 3 ways to write cosine 2 row. We could do cosine squared row minus sine squared row. Or I could do 1 minus 2 sine squared row. Or I could do 2 cosine squared row minus 1. Make sure you have these memorized. Looking at the other side, I only want sines. Which double angle cosine should I choose, Chris?
The sine squared of row minus 1.
Look it up. Flip back a page in your book. Or 2 pages. What's my double? That's half angle. Sorry. Flip back another page. What's my double angle for cosine that I want?
1 minus 2 sine squared.
1 minus 2 sine squared, in this case, row. Make sure you have them memorized, because if you don't got them memorized, you can't do squat. All right. Now right here. What is 2 times sine times cosine times cosine? What's an easier way to write that?
2 sine cosine squared.
2 sine row cosine squared row. Yeah, no problem. They're just like 2xy is 2xy squared. Well, this is 2 sine cosine cosine. 2 sine cosine squared. But here, Quentin, I do have a polynomial times a monomial. So here, I should distribute to get
Sine row minus 2 sine cubed row.
So far, so good. Now, as we look at this left-hand side, and then we look at where I want to end up with on the right-hand side, there's one thing that really doesn't fit in at all. What's the one thing that is really just a misfit? Ethan? Speaking of misfits, just kidding. Ravens fan.
Oh, come on.
Just because they're the best team in the AFC right now. Oh, unless, no, the Titans. Titans still are. They knocked off the Rams last night, didn't they?
Yeah.
It was 21-3 at halftime, so I didn't bother watching it, but
Yeah, they beat.
Someone got
Dallas
dismissed.
lost, and all their points were garbage time points.
Someone got smacked by the Browns.
Cincinnati Bengals, who got beat up bad. And the Jaguars.
Yeah.
How about those Jags beating the Bills? Now I'm scared because I was like, yes, at least we have the Jags next week. Colts
Cowboys
go to
lost.
5-5. No, we got the
Cowboys lost.
Cowboys lost to the Broncos. What happened yesterday? It was weird. Chiefs did beat the
They did.
Rodgers-less Packers. Yeah.
They did.
Mm-hmm.
Scored.
It was low. It was bad. Anyway, let's come back in. But who's the misfit, Ethan?
Me.
Yes, you.
Missed it.
Rudolph.
Island of
Was a
Misfits.
dentist.
I was
Yeah,
like,
I was
no.
thinking the whole
Who's
time.
the misfit?
We don't need a cosine square.
Right, the cosine square is the misfit. Everybody else looks happy, but not the cosine square. So how could I rewrite cosine squared so poof, it becomes sine?
You can write it as 1 minus 2 sine squared.
Ooh, you're thinking of a double angle. This is just a cosine square.
1 over sine.
I'm thinking Pythagorean.
Yeah.
Let's not forget our
Yeah.
old identities.
Yeah. 1 minus sine squared.
Good. Sine squared plus cosine squared equals 1, right? Don't lose track of your fundamental identities. Got to remember those. So if I move the sine squared over, that's what cosine squared equals. So let's put a 1 minus sine squared row in place of the cosine squared row. Now you see how everybody is sines? Now we're happy. But once again, Quentin, I have a monomial times a polynomial. See, you were excited about this, so we had to work a couple of those in for you.
Not yours.
So what do we get, Quentin?
2 sine row minus sine cube, or 2 sine cube row.
There we go, plus we have the sine row here, minus 2 sine cube row. Now what? Chris?
Do the math.
What?
Negative.
It's really fun.
So 3 sine row minus 4 sine cube row.
I'm running out of room. Thoughts, Jamie?
We're finished.
That's what we wanted, which is really good because I just ran out of room.
You need your chair, you know.
I could, but I just stand back up in a second anyway. Questions on this? Do we see how to handle a triple angle?
Of course not.
And we saw how to handle a quadruple angle. Double a double. Triple is double plus single. So we got this. We can do this.
Let's stop right here.
Yeah.
All right. Next thing in your notes. Half angle identities. Half angle identities. I'm going to talk fast. You listen fast.
Yes, sir.
Because we only have 5 minutes.
Yeah, we're running out of time. Well, we got until I stop, but you know.
Yeah, I know. Yeah.
The next class who wants to come in might be upset. All right, so half angle identities. Next thing in your notes, half angle identities. I want you to consider this for just a moment. Imagine if I took the cosine of theta, which is just nice and easy, and I just had to be like Quentin. I just feel inspired by Quentin. I'm like, you know, a plain old easy theta could be rewritten twice a half theta, and that would still be the same thing, right? And of course, we know that the cosine double angle could be written 1 minus 2 sine squared half theta. Correct? So that means the cosine, in all its simplicity, I could extrapolate 1 minus 2 sine squared half theta, right? And if I saw fit, because this is a negative, I could double switch to say that 2 sine squared half theta equals 1 minus the cosine of theta. Furthermore, I could divide away the 2. I could take the square root, and because I took the square root, I have to put a positive negative. So I could say that the sine of half of theta is positive negative square root of 1 minus cosine theta all over 2. And there's the first thing you need to write down. Not all of that, just this. The sine and half angle identity is positive negative the square root of 1 minus cosine theta all over 2. Now, if I saw fit, I could also write this as 2 cosine squared half theta minus 1. At which point I could double switch well, I could just move the 1 over. Move the 1 over as a positive. And then I could divide away the 2. And I could take the square root. And that would give me the cosine half angle identity as positive negative square root of 1 plus cosine theta all over 2. Now the good news is, Christopher, these match. They're the same, except one's a minus, one's a plus. You just got to remember which one's which. I think of it as sine is always an odd function, so sine has the possibility of a negative. That's not why it works, it just happens to be there. And cosine's even, so cosine's always positive. That's how I remember cosine has the plus and sine has the minus, but whatever. And furthermore, you know that the tangent is always sine over cosine, right? So if I were to put the sine above the cosine, those two denominator 2's are going to cancel, right? To get plus or minus the square root of 1 minus cosine theta over 1 plus cosine theta. And there's your tangent half angle identity. You're writing these down. However, if I saw fit to rationalize the denominator, if I multiply it by the conjugate 1 minus cosine over 1 minus cosine, I get 1 minus cosine quantity squared over 1 minus cosine squared sum and difference, which 1 minus cosine squared is sine squared. So 1 minus cosine squared over sine squared, square root of all that just comes out to 1 minus the cosine over the sine. Poof, the radical's gone. Put a star next to this one. This is my favorite, because there's no radical. no radicals.
It's pretty radical, man.
Now, if you're demented, you can multiply top divided by 1 plus cosine, which will give you the conjugates in the top, which will give you 1 minus cosine 1 squared, or 1 minus cosine squared at the top, which would be sine squared, over 1 plus cosine quantity squared, which takes the square root, could give you the sine of theta over 1 plus the cosine of theta, but I don't know why you want to do that. But you could. 3 forms for tangent half angle. Just like there were 3 forms for cosine double angle. And these you will want to have memorized for Wednesday, lesson 65. For homework this evening, you're going to copy each of these 2 times in preparation for a quiz coming up in lesson 65 on Wednesday. You'll want to make sure you know your double angle for sure by then, but you already know those pretty well. And of course, these half angle identities. You'll want to know those also. Of course, you don't want to forget your Pythagorean or your quotient or your half negative angle or your reciprocal or your sum and difference. But in addition to all your fundamental identities and the sum and difference identities, you want to know your double angle and your half angle identities. For Wednesday, lesson 65. That's your only homework tonight, is to start working on memorizing those as you copy them 2 times each. Have a wonderful rest of your day. You are dismissed. Thank you.